All right, we're going to go ahead and keep this picture here. We'll go ahead and jump over and start looking at the class code for this. Okay, so far I've been writing out the class code, at least in a standard way, of just stubbing it out. I'm going to try and help y'all with understanding unit tests a little more and actually show you how I can integrate them inside of our class code. So I have a little template that we have created from earlier. And we'll move, oops, testing template, everything to here. Okay, and this is just a similar testing template that's inside of your labs. So the first thing we need to look at is what are we going to, or how do we actually create this binary tree? So source binary tree.hpp. It's always harder when someone is watching. All right. Now we got this stubbed out. What do we need in our binary tree?
A node.
A node.
2 pointers.
And 2 pointers. So we need to create a node class first, right? All right, let's go and do that. What's inside of our node class?
2 pointers.
2 pointers to
Left and right.
to left and right. All right, we'll go ahead and call this a binary node, binary tree node to be more explicit here. So we'll go ahead and create a public binary tree node m left and m right. What else needs to be in this node?
It's data, right?
It's data. All right, we're going to make this easy for us, and we're just going to store integers for the time being. Okay, simple enough. We'll create a quick constructor to initialize all the variables real quick. And then m left, what should m left and m right initially be? Null, yeah. All right. So now we've defined what a node is. What do we need in our binary tree?
Beginning.
Yeah, the root. So we need to have something that points to the root. All right. So we have, let's see, binary tree node m root. All right, it's always good once you type a little bit to see if it actually compiles. Yeah. We should also make a CPP file just to test it. So tab new source binary tree.cpp. All right, and now we can at least test, make sure the code works. That's testing with our main, so we want to test at least with an empty test. We'll go ahead and create a quick little, well, we have the empty test. So we'll go ahead and start with that one. Notice I'm just using the empty test that we have from beforehand and including the HPP just to make sure our code makes some sense. Good. Even include the CPP. All right, so at least it compiles. All right, so the binary tree is supposed to act as replacement for a linked list and array. What do we want to, what functions do we want here? Insert, all right. Those probably should be public. What else might be handy? Remove, all right. We'll make that a Boolean because it may not be in the binary tree.
Search.
Search, all right. We'll call it exists. All right, so we have insert, remove, exists. All right, I think that's pretty good for now. We're going to get into a couple more capabilities in a moment, but right now I think that'll be a good thing to start off with.
Do we need, I know with the other data types, data structures, we needed a link, a global link variable.
Global link
Like in size.
Sure, we could keep the size.
I just didn't know if we needed that.
We could keep the size. That's not a bad idea. That's nice because a lot of times you want to know how many items are inside your data structure, so sure. All right, there's one very important function we're missing before we start implementing. Actually, there's two, but what's the first one?
Yes.
So we actually need to construct the
There we go.
tree.
We need to construct this tree. And then if we have a constructor, we need, there we go. All right. Okay, so we'll go ahead and put these over here. All right, let's see if that actually typed out correctly. Looks like we're doing great. All right, so at least we have these stubbed out. We should look at our test cases first. That way we can at least come up with a scheme of what we want to be implementing. So let's jump over here, and we have currently our empty test. So let's go ahead and create a, what's the first thing we should test here? Probably adding something and then asking if it exists in there. Good standard first test case. So we'll go, let's see, exists -test.cpp. Then we'll jump back over here, tab new, tests exists.cpp. Perfect. All right. So test one, we probably should create a binary tree. And just to make our lives easier, we'll go ahead and create it on the stack. I'll just call it binary tree for now. Probably what we want to do is bt.add, what's some values we want to add? 12. 4. 8. Sometimes I get some funny ones like 9,000. Those are my favorites. Whoops. All right. So let's go ahead and do a quick little test case. TS assert bt.exists sub. Well, should 12 exist? Yeah. So we want to test to make sure that one exists, and then let's test that something does not exist. We'll do -100. All right. Good starting test case. Let's see if we actually wrote that correctly. Let's see, exist-test. No member add. Do we not put it in our HPP? What do we call it? Oh, we called it insert. No one caught me? There. All right. 0% success rate. Probably accurate since we have not implemented anything. All right. So now we have at least a basic test case. We can start putting everything together. All right. What's the first thing we need to do in the constructor?
Make a root.
So if we have an empty binary tree, is there going to be a root?
No.
No, but we still need to do something with root.
Initialize it to.
No, there you go. Yep. We'll come back to the destructor later. Put a to do once we understand how the whole data structure is set up. Okay, here we go, insert. How do we insert something? Well, what are the different cases?
But if it's empty, you can just set the whatever whatever the first thing you insert to in root, and then just have its
Okay.
children be null.
So if empty, set the root to, what are we setting it to?
The value.
To value? Before we create the value, what do we actually need to create here?
The node.
The node, yeah, we need to create the node. All right. 1, create a node with value. Then 2, if empty, set the root to the new node. All right. And then we'll go with and exit. But if we're not empty, what do we need to do?
See, it's less than or greater than the root.
See if it's less than or greater than the root, right? And then
Add it based on that.
add it based on that. So we need to, overall, we need to find where it needs to go, right? Yeah. Find the loop. And then once you find the location, we'll go ahead and all right. So create the new node. Let me go ahead and get this started. So binary tree node. Ooh, is it going to be on the stack or the heap? We put it on the stack. When does the node disappear?
At the end of the function call.
At the end of the function call. Do we want that?
No.
No. So it's got to be on the heap. All right. So therefore, it needs to be a pointer. And we need to actually create it out in memory. Now, if you recall, the constructor here set the left and right to null for us, so we don't have to do that, but it set mval to 0. Is mval going to be 0? Probably not. There's a 1 out of 4 billion chance, roughly, but not a good chance to take. All right, so there, we've created the node. Perfect. Are there any questions on this, what's happening here? We have a lot of problems with pointers, so just want to make sure it's clear. Okay. So if mroot is null, what check is that?
Make sure it's empty.
Right, so if it is empty, what do we need to do? Set it there, yeah, so we go. I'm going to space this out a little for you. And we are going to return here because we don't want to continue. It's already inserted. So we go ahead and insert the new node and then exit. All right, great. Find the location of the new node. This part is actually very hard. So let's look pictorially what we're going to do here. So if we want to find the new location, let's say we have this binary tree, and we want to insert 52. Where would it go?
Left of 58.
Left of 58. How would we get there?
Less than or greater than checks.
Less than and greater than check. So, but where would we start?
The root.
The root, which is 60. So we'd first start at 60. And we'd ask if it's less than or greater than go to 50, less than or greater than go 58, and then we'd be done. Have we done this before with pointers? Okay, I have a rhetorical question. We've done this before with pointers, sorry. Can you remember what we used? What do we call the variable?
Rover.
Rover, yeah. I usually call him Rover. You can call him something else, but I like calling it Rover. So we'll have a binary tree node star rover. And where does it need to start? Yeah. Okay. So we have a rover. It's going to point up here. And we're going to basically be checking if it's less than or right. So let's go ahead and write that check in just so we have a piece of code. So if rover mval is less than, I'm sorry, is greater than mval, then which way does rover need to go? Right, so it'd have to go to the right. So then rover equals rover m right. else
Rover go to the left.
rover goes to the left.
Well, which way do you go if it's the same number?
Great question. That is a bit of a trick, and it depends on your data structure. If you have to make a choice of whether you want your data structure to contain multiple instances of the same variable or not. So if it's not supposed to contain it, then once you find something that's equal, you exit and say the insert failed. But if you wish to contain more than one, then you can go ahead and go down the list and find it. We haven't talked about sets and maps yet, but the idea is in a set you only have one unique element per inside your data structure, but with the map or other types of data structures you may have more. So it really depends. For now, let's just guarantee that that situation doesn't exist. We'll get to that later, but that's a great observation. All right. So we're ignoring, and I'll go ahead and write that in. We ignore, actually, it is guaranteed that all values are unique. There we go. Okay, obviously this is only going to happen once, and
The worst speller ever.
I am terrible. I
I
really wish they could do auto check inside of Vim, but it doesn't happen. Is that 2 R's or just one?
No, it's not 2 hours a
It-
guaranteed.
There are.
It's okay.
We know what you mean.
It's in the comments. It's very Texas spelling.
How's that? How's that? Is that better? Better now?
Nice.
Nice. Okay. Obviously, this check's only going to happen once, so we need to make it happen any number of times. So we need to put in a loop. What are we checking?
Should we check until rover is null?
All right. That's a good start. While rover does not equal null. All right. What's that going to do, though? So at the end of this while loop, what's rover going to be?
No.
Null. Do we want that?
No.
No. We want to have the parent, right?
So do we do while rover, like while rover's in left and in right, like while the children are null?
So while the children are null, so if both children are null, then
Or if one of them is null?
if one of them is, yeah, but how do we know if that's the null we want?
That's also true.
That's true. This is actually a situation where the iterative solution is confusing, but we're going to stick with the iterative solution for now. Okay. Sometimes if things are actually confusing, it's good to have a flag variable to flag when you're done. And for now, we'll just have Boolean is found equals false. So now inside this while loop, we'll have while not is found. So basically, we just want to set found to be true when we've actually found the location and then exit out of this while loop. This will hopefully make the code a little easier to understand right now. So now let's go back and look at our if statements. If the value is greater than val, in what situation do we want to check? Do we actually want to move rover?
If found is true.
So if it's greater than val, we only want to move to the right if the right actually exists. So. Right? Now we are going to have to put a little check here. mval is less than mval, and we're going to do the same check. So in other words, if we can go right, go right. If we can go left, go left. If we can't go right or left, then what have we done?
You're at the root.
You're
Or
at
not
the
the
lead.
root, but the parent.
Yeah, you're at the parent of the actual node. And so we want to end the while loop, so we'll just say is found equals true. Okay. Hopefully that won't go into infinite loop, but we have test cases to find out. Any questions about this? It's a lot cleaner than the recursive algorithm, which we'll get to in a moment. All right, so now we need to insert in the location. And this is just simply another check. If rover mval is greater than mval, mright equals new node. So if it is greater than, we put the new node to the right. Otherwise, we put it to the left. Yes?
I have a question. Wouldn't if it did go like in that other one that we were just doing, if it did pass either one of those else, like the if or the if, it would be would it be an infinite loop because we're not changing is found in either of those.
Ask your question again?
So like for those we're not changing is found, we're doing that in the else all the way down here.
Mhm.
So wouldn't it be an infinite loop because we didn't change it if it like passed that test case?
Okay, so think about what's happening here and what we intend to happen. It's going down the tree, right?
Mhm.
It's either going to go jump down the tree or say we're done, are the two options, right? The first two are we move down the tree, the other one we're done. The tree is finite, right?
Yeah.
So it eventually has to go down and find something.
Okay.
Okay? At least, hopefully that's what our code is doing. That's what we intended to do. All right, so this function is actually fairly complicated. Well, let's see if at least compiles. Not quite. Let's see what we got here. I was using the word val, mval, when in reality I meant to use the passed in value. Everyone see that?
Yeah, you have it up there.
Yeah, I think, did I get both of them? Nope. On line 30. Ah, yeah, right here. Okay, good. Success rate's still 0, probably because we're not doing exists correctly. All right, so we'll skip remove for now. That's actually a little more complicated, and we're going to do that next class. So now we want to do exists instead. All right. So how do we find out if something exists in the binary tree?
We would have to iterate through the find the val and then go to the left or right depending on what it was.
Okay. So one, iterate through, whoa, that was terrible. Whew. At least caught that one, okay? All right. Do I get it? Am I okay?
One
Okay.
syllable words.
All right, we're iterating through the binary tree. What'd you say, going left and right?
Yeah.
Going left and right. Okay, going left and right. Okay. Then what else do we do?
We have to check the val.
Okay. Check val when?
When we get there?
At each position, maybe?
Yes.
Yes.
Yeah, that one.
Slash node. All right. Actually, we should put a check at each position. If found, return true is what, whew, return true. All right, what happens if we go through the whole thing and we can't find it? Return false, all right. So we'll put that at the end, return false. All right, let's go ahead and jump up here. Well, we've already written the code for iterating, so let's go ahead and copy paste that real fast. And we actually don't want to do this whole is found thing. I think the old section of finding out rover does not equal null is going to work. And we don't need a semicolon. So we'll go ahead and simplify this a lot. Whoa.
Should the first thing you check in this be if root equals val, or yeah?
That's true. We could first check if root equals val, although we are setting up a loop that's going to start at root and then continue on. So inside the loop,
Okay.
we actually need to check if it's equal to val. So that's actually the first thing we should check. We'll put that comment right here. Okay.
So
Actually,
are there like indexes for these values? Like, could they ask for an index of something in a binary tree?
you would have to come up with an ordering in order to do an index. And that's a great question because we're going to get to ordering in a little while, but not yet. All right, hopefully this code works. Anyone see any issues, or go ahead and test it? Give it a shot. Why not? Oh, hey, look. Looks like it's actually working correctly. Well, at least we have some confidence that it's working. And actually, if I look at the code, I think we did go about it a correct way, I should say. All right. Let me pause here with the coding, and we're going to get to very important performance.